Hello, in this lecture we are going to begin our analysis of quantitative data set of a single variable. The objective for this lesson is to represent quantitative data graphically. First, let's remind ourselves of what exactly constitutes quantitative data. These are data that are numerical, and taking the average of them makes sense. Remember, we also have continuous data, which represents data that can basically take any numerical value in a range, and discrete data, which has clear gaps between values. Now, these concepts are more for theoretical distributions, not experimentally created ones like what we're going to be dealing with today. So this distinction is not going to be our focus. Now, for the next few lectures, we are going to take a look at the performances of my students in the past. Why? Well, remember that for any statistical study, we need to first ask a question. And my question is simple. Did my students perform well on their final exam last year? Let's take a look. Here's a set of scores on a final exam from 33 kids in a first period class. Notice the set is already organized from lowest to highest score. Because hey, working with organized data is easier pretty much always. Now, this test was out of 70 points. If I wanted to, I could break this down into a frequency table of who got A's, B's, C's, and so on. But we've already done that with some in-class examples. I could, on the other hand, look at student by student. But I don't want to do that. That's a lot of work. I want a general summary of how my students did. For that, we will want to create a graph. Now, there are a plethora of quantitative graphs we could make. For this lesson, we're going to focus on 3 of them, and they are dot plots, stem plots, and histograms. Each has their own advantages, but generally they are all acceptable and appropriate for quantitative data. So when I give you these reasons why you might choose one graph over the other, don't take that as a strict rule, but more of just a suggestion. First up, let's look at the dot plot. Now, the dot plot is beneficial when you have a small data set, meaning not very many individuals, or you don't have very much variability in that set. For example, if I wanted to graph my students' AP test scores, I would only have a possible score of 1, 2, 3, 4, or 5. Now, that's not much of a range, so a dot plot would be very clear in this case. Now, the dot plot is simply just a horizontal axis that is scaled and labeled. Each individual data point receives a mark on that axis. Now, that mark can be an X, like I have here, maybe a square, a star, or a dot, hence the name dot plot. I personally like X's because they are easy to make the same size and stack on top of each other consistently. And that consistent readability is what we really want in a dot plot. So how do we make one? First, draw that horizontal axis. Second, set a scale based on your minimum and maximum values. Remember, give yourself a little bit of headroom, so set your first and last marks generally a little lower and higher than your most extreme individuals. Third, place a mark for each individual. Individuals with the same value should have a mark placed on top of each other. Fourth, add a title to the axis. Now, the main advantage of a dot plot is that they are very easy to create. You don't have to think about it too much, just be accurate. If you have a moderately large data set or you have more variability, you may want to create a stem plot. We'll graph the same set of data for this so you can see similarities between the graphs. A stem plot consists of 2 components, the stem and leaves. The stem consists of all but the final digit of a data value. Each leaf is then the final digit of that individual value. The leaves are then placed in order from least to greatest, extending out from the stem. The advantage here is that it does a better job of summarizing a set as it groups individuals with similar values. If your data set is in order, this is even easier to construct than a dot plot. To make one, start by listing out your stems vertically in order. Remember, this is all but the last digit. So my stems in this example represent the tens place. Next, draw a vertical line to separate the stem and leaves. Then start writing out your leaves in order. Separate each leaf with a space. Don't use commas, decimals, or anything else, just a space. Next, make a key that identifies the variable and provides an example of how to read the graph. Finally, make sure you have a title. Now, with a very large data set, or if you have very long stems, you can actually make it more readable by creating a split stem plot. Here, you have 2 duplicate stems. The first stem is for values terminating in numbers 0 to 4. The next stem for values terminating in numbers 5 to 9. But now we're still not done with stem plots because there's one more that you can make, and that is called a back-to-back stem plot to easily compare 2 distributions of similar variables. The same rules here still apply, except now your stems are going to be in the center of the graph, and you'll have leaves extending to both the right and left of the stems. No matter which side you're on, the leaves extend out in ascending order from the stems. All right, now we're done with stem plots. Let's move on to histograms. First things first, this is not a bar chart. A bar chart, remember, it represents qualitative data. A histogram represents quantitative data. The main visual distinction here is that there are no gaps between the bins. The space between bins and bar charts gives your reader an indicator that they are looking at categorical data. If you start including gaps in histograms, it will appear that you are misrepresenting your data. More on that in the next lecture. Histograms are really just stem plots that have been flipped on their sides with a little bit less detail. They're a good choice when you have a lot of variability, maybe a very large set of data, or you want flexibility in highlighting certain trends. So how do you make a histogram? First, choose equal bin widths by dividing your range into a reasonable number of bins. In my example, my tests were out of 70 points. I wanted to separate them by groups of 10 points. So I took 70 points and divided by 10 points in each group, and I have 7 bars. There's no set rule for how many bins you should have. It's up to you and your data set to make that decision. 5 is a good number of bins to go with. You see, if you have too few, you're not going to notice trends in your data. If you have more than 10 or 15 bins, however, your trends also start to disappear again, and your graph becomes really difficult to read. So it's up to you to make the most logical choice based on the data you have. Next, make a frequency or relative frequency table to group your data into those bins. Frequency is here the most common choice. Once you've done that, draw, scale, and label your axes. You see, a broken line on the x-axis is okay, so you're not wasting space. What we mean here is start the scale of the x-axis close to your minimum value. For example, if I wanted to graph the points scored per game by teams in the NBA this season, my minimum is 102.9. So when I make my graph, I start at 102, not at 0 on the x-axis. That's otherwise just a big waste of space. Your frequency axis, however, still always needs to start at 0. Finally, draw your bars, start those bars on the tick marks of the x-axis, and then end them at the very next tick mark. No gaps in between. And guess what? That's it. We'll focus on other quantitative graphs in another lecture. Today, however, we learned how to create dot plots, stem plots, and histograms. Join me in the next lecture for quite possibly the most important skill of the unit, and that's describing quantitative distributions. Thanks for joining me. I'll see you next time.